Hello everybody, this video is on back EMF for DC motors. As we discussed on the introduction video to DC motors, a motor is a device that will convert electrical energy into mechanical energy through producing rotation via the motor effect. As the armature of the motor rotates, the armature will experience changes in magnetic flux. This is because magnetic flux, or phi, is given by B multiplied by A multiplied by cosine theta. The angle theta is the angle between the normal that's drawn from the plane of the armature and the direction of the magnetic field. So when the armature is parallel or horizontal to the magnetic field, this angle here between the normal and the plane of the armature is perpendicular or 90 degrees. Now, as you can imagine, as the armature rotates, this angle that's between the normal and the direction of the magnetic field will start to change. In this case, it will increase from 90 degrees. As the angle theta in my formula for flux changes, the amount of flux that's passing through the area of the armature will also change. By Faraday's law of induction, when an armature or conductor experiences any changes in magnetic flux, an EMF is induced in the coils of the armature. In Faraday's law's equation, the magnitude of EMF is directly proportional to the rate at which the flux is changing. That means if the motor is rotating faster, there will be a larger EMF induced in the armature. This EMF that's induced due to the rotation of the armature is what we call back EMF. The reason why we give the EMF this name is due to Lenz's law, which states that the current induced due to the EMF as a result of Faraday's law will flow in a direction such that its magnetic field or magnetic flux will try to oppose the changing flux which produced the EMF in the first place. The induced current due to the back EMF will produce an opposing force that will tend to reduce the rate of flux change. As a result of this opposing magnetic force, the armature's motion will be opposed. So if we have an anti-clockwise rotation of the armature due to the motor effect forces shown by the black vectors, the back EMF will produce its own opposing forces that will counteract the rotation. So that means the torque acting on the armature will reduce due to the back EMF. We'll talk more about torque and back EMF in a moment. A very important concept that I want to reiterate is that the magnitude of back EMF as a result of Faraday's law, it increases with the motor's rotational speed. As the motor speeds up, as it starts to rotate faster and faster, the amount of back EMF that's induced in the armature will become larger over time. And this is represented by the first part of this graph. As the motor rotates with time, it increases in speed and the back EMF increases in magnitude. The back EMF will, like we said, due to Lenz's law, will produce an opposing force. The magnitude of this opposing force is proportional to the induced current, so that will also increase with the rotational speed and time. The operational speed, so this is the constant speed at which the motor is usually functioning or operating at. This speed is reached when the opposing force, due to the back EMF, balances or equals to the magnitude of the motor effect force, which provided the torque for the rotation of the motor in the first place. So after some time, when the opposing force due to the back EMF balances the motor effect force, the rotational speed of the motor will become constant as there's no longer torque acting on it, and this is when the motor reaches its operational speed. Because the speed of the motor determines the rate at which the flux is changing, the back EMF will no longer increase and it will stay a certain value. What you also need to know about back EMF is that it will reduce the overall magnitude of currents that's flowing through the armature. The direction of back EMF is always the opposite to the EMF produced by the DC power supply of the motor. So as the motor starts to spin faster or starts to rotate faster, the back EMF increases as we discussed. That means the total EMF decreases, and by Ohm's law, which is V equals to I times by R, as the total voltage or EMF decreases, the size of the current flowing through the armature or coils will also decrease. So initially, when the motor has just been turned on, the current flowing through the coils will be the highest. As it starts to rotate, there will be changes in flux, which induces the back EMF, and the back EMF will reduce the current that's flowing through the conductor. When the motor reaches its operational speed, so this is when the force due to the back EMF balances the force due to the motor effect, the motor will reach a constant operational speed. At this operational speed, the rate of flux change will remain constant, and so the magnitude of back EMF will no longer increase, and it will also remain constant. So that means the magnitude of current flowing through the coils of the armature will remain constant as well. The magnitude of torque is heavily associated with the magnitude of current because the two variables are directly proportional. As current increases, the torque increases. As current decreases, the torque on the armature also decreases. As we said earlier, at the beginning, during the startup phase of the motor, there is no back EMF. And this is when you have the greatest current flowing through the armature. And when you have the greatest current, you also have the greatest torque acting on the armature. As the rotational speed of the motor or the armature increases, the magnitude of back EMF also increases. An increase in back EMF results in a decrease in current flowing through the coils, and as a result, this will decrease the magnitude of torque acting on the armature. This is why, on a torque versus rotational speed graph, the stalling torque, which is the torque acting on the armature when it is not rotating, is the highest, because this is when the back EMF is zero, and when the magnitude of current flowing through it is at its greatest magnitude. The torque decreases as the motor starts to rotate faster and faster due to larger back EMF. And this is because, again, larger back EMF means you have a decreased current and decreased torque. When you get to the maximum angular speed, so this is the fastest speed at which the motor will operate at, this is when the back EMF is the greatest. And the opposing force from the back EMF will balance the force due to the motor effect, giving a net torque of zero. This concludes the video on back EMF in DC motors.